So our next speaker is Dr. Anil Kakodkar, who is going to talk on harnessing thorium for nuclear power, challenges ahead. Dr. Kakodkar is again known to everybody here, but still he is the former chairman, Atomic Energy Commission, and is currently holding the Indian National Academy of Engineers Satish Dhawan Chair of Engineering Eminence at BRC. He is well known personally for his contribution in various aspects in the nuclear energy field. He has worked on self-reliant development of nuclear reactor systems to address India nuclear program requirements. Several new technology areas such as accelerator-driven systems, high-temperature reactors, materials and recycle technology, etc., have all been initiated by him. May I request Dr. Kakodkar.
Chairman, ladies and gentlemen, after Dr. Sinha's talk, my job is pretty simple, and I have a single point agenda, and it will be clear to you by the time I finish, which I hope won't be very long. Now, we are all aware of the role thorium can play in variety of ways, quite apart from the fact that thorium by itself represents a large energy resource. But at the same time, we are also witness to this fact that, well, first of all, there are barriers to growth of nuclear power. We have been seeing this time and again. Every time it appears that nuclear power is on the upswing, and then something happens and the growth really is there, but it's pretty slow. And in the context of thorium, of course, the picture is even more. We are all thorium enthusiasts, so please don't misunderstand me. I'm an equal enthusiast of thorium. But when we see what's happening on thorium, sometimes it appears very depressing. So, and then of course in conferences like that, we make one more attempt, essentially to convince ourselves. This is one more such attempt. Now, before going for talking about thorium per se, the International Energy Outlook published by Energy Information Administration 2013 is the latest document that I could lay hand on. It says that the world energy consumption will grow from 524 quadrillion BTUs to 820 quadrillion BTU between the year 2010 and 2040, which corresponds to a 56% increase in the installed nuclear generation capacity. Now, the projections are that most of this growth would happen in non-OECD countries. As you can see, this is OECD, that is. So, the happening place is the emerging economies, the developing worlds, and the OECD countries, they're already sitting on a more than necessary access to energy. And so obviously it's not going to grow much there, although there will be nuclear power addition, but net energy is unlikely to grow very much. And so we have to really focus on non-OECD countries. We've been talking about green scenario, renewable energy growth. The projection of the international energy outlook is that during the same period, that is 2020-2040, the relative share of non-fossil, and that includes renewable as well as nuclear, non-fossil energy is likely to increase from 16.5% to 21.4%. Now this actually means that the share or the CO2 emission would actually increase by around 40%. We're all aware that everybody is expecting that we should limit the temperature rise to around 2 degrees Celsius. Now, I actually participated in a climate change gaming exercise. It was a work done by several countries, and these exercises were held in India, China, UK, and perhaps United States. And this was to look at how different countries would respond to different state of happening and what it will mean in terms of the climate change. And I was actually shocked in all those scenarios which happened by way of decision taken by different players who were playing for different countries. 2 degrees Celsius above the old threshold appeared impossible. In fact, people are reconciled to even 4 degrees Celsius, some even more. And in most of the scenarios, it was observed that we are actually heading towards a very serious situation from the point of view of security and global stability. Now, I hope the next round at Paris, some sense prevails. The intended nationally determined contributions which all countries have announced, I suspect are actually not adding to what the goal should be. And so that's the backdrop in which I want to address whatever I want to address. Now, mind you, all this is happening in the same time frame which I'm talking about. So we may have ideas about development which may come on the scene 20, 30 years from now. In the sense they may start contributing 20, 30 years from now. If the climate change predictions are right, if that the science or the modeling which has been done is right, then I think I put it to you that that will be too late. And I think we need to do something concrete very fast. And please look at what I'm trying to say in that context. Let me for a minute talk about Indian scenario, Indian energy scene. India, currently we are using, and this is total energy, mind you, not electricity. You know, many times we get talking about electricity as if that's the only energy. Electricity constitutes, depending on the state of development of the country, constitutes maybe 20-25% at best of the total energy use. So there are, the energy use is much larger because there are other segments of energy use other than electricity. So I prefer talking about in the context of oil equivalent. And so in India we have currently around 640 kilogram oil equivalent use, which amounts to something like 0.82 billion tons of oil equivalent annually. Most of the oil, some gas and some coal we import, the import of energy is likely to rise sharply. In 15 to 20 years, the projection is it's likely to become 5 to 7 times what we are importing. So even from pure economic consideration, it's, in my view, a dreadful scenario. We are a developing country. We have our own development aspirations. And there is a correlation between energy use and human development index. We would also like to reach a human development index corresponding to the advanced countries, which would mean 0.9 plus. If you want to achieve that, allowing for the statistical variation, we need to reach our per capita energy consumption to around 2,500 kilogram oil equivalent, which with the higher population which might exist at that time, whenever it happens, would correspond to something like 4.1 billion tons of oil equivalent energy use. So when we are talking about future, we have to look at an energy use of that order. The total primary energy reserves restricted to coal, oil and gas in India have been estimated to be around 361 billion tons of oil equivalent. But the actual mineable quantity is likely to be, in fact, much less. And actually, this is a technology challenge to make better use of our available oil resources, both in the context of coal as well as in the context of oil. In fact, only the other day I was talking to one of the international experts on oil exploration technology, and he said getting larger oil from ground, actually, of course there are many factors to that, but one important factor is to create a low-cost surfactant to improve the recovery. And today, of course, most of the surfactants which are available for use, the cost is much larger. And so we are not recovering as much as one would like to recover. So this primary energy may last us at the equilibrium use maybe 4 decades, 5 decades, or something of that kind. If you look at renewable, except solar, but I have included the large hydro also in renewable, the total potential is estimated to be around 300,000 megawatts, 300 gigawatts peak, which translates to around 0.2 billion tons of oil equivalent per year, which is actually around 5% of the requirement. So we should make use of it, because today we need all energies, but not very large. Solar, of course, is abundant, and if you consider the total landmass, Indian landmass, then you can get several orders of magnitude more energy than we need, but that's not possible. But even if you are able to divert 45,000 square kilometers, which is roughly 1/4 of the barren uncultivable land in the country, we should be able to produce enough electricity to meet the entire nation's need at those higher level of requirement. So this is something I think we should certainly emphasize on, and that's what the country is doing. But we need emphasis. I think it's all emphasis on photovoltaic. We need emphasis on solar thermal, because, as I said, we need to use solar energy for producing electricity, but we also need solar energy for producing other forms of energy. And their thermal energy at high temperatures is very important. As it is, solar energy doesn't give you a steady supply. There is a storage issue. And so it's clear that as far as India is concerned, nuclear energy is in fact inevitable, sooner or later. And within nuclear energy, because of our modest uranium resources, thorium becomes very important. And of course, if you want to use thorium, you cannot use thorium unless you have adopted recycle technology, which of course for very sound reasons we have right from day one. And so use of thorium, barring of course the technological difficulties, which of course we are overcoming one by one. So I think we are, in my view, well poised to make use of thorium. So going forward, as far as India is concerned, the 3-stage nuclear power program leading to thorium is actively being pursued. Considering the rapid growth in energy needs, rising import burden, and climate change concerns, deployment of non-fossil energy source need to be accelerated. For us, the need is now, and need to bring in energy conversion technologies to facilitate use of non-fossil primary energy in all segments of energy use, and which would mean splitting of water, using hydrogen and biomass to produce hydrocarbon substitutes, and so on and so forth. And this is a whole range of technologies where, in my view, we are not paying adequate attention. And I think we should put this a challenge before ourselves, that primary energy for India in long term means thorium and solar, and do every bit to convert that into electricity, as well as all other energy forms that we need today or we would be needing tomorrow. As far as the global scenario is concerned, the global fossil energy sources are likely to be severely stressed should a significant fraction of population in emerging economies start consuming energy at the same level as advanced countries. You can just do a back of envelope calculation. Assume that 20% of India and 20% of China uses energy at the same rate as Western countries, and you will find that there is a huge energy crisis right there. And so now nuclear power, of course, we know it's growing, but it's growing rather slowly. And we also know, I had made a presentation in last Thorium Energy conference. Dr. Sinha mentioned several points here. We know that thorium can soften some of the barriers to growth of nuclear power. And I think that's what I want to emphasize on. And of course, thorium, of course, is more abundant than uranium. So moving towards thorium and using uranium and thorium with some kind of synergy will in fact enlarge our energy basket much more. In terms of the projected growth, we talked about this, but just some information which I picked up from the WNA site. There are 435 commercial nuclear power plants operable in 31 countries, totaling to 375 gigawatts of capacity, which is 11% of world electricity production. But that says more than about 70 more reactors are under construction, equivalent to 20% of existing capacity, while 160 are firmly planned, equivalent to half the present capacity. And then there is, on the emerging nuclear energy countries, there is a list, and what I have listed here seem to be more probable countries, but plus there are 43 other countries. Now this looks very rosy, and we have seen such reports even earlier, but in reality it doesn't really move that fast. And as was said earlier, the growth in nuclear power deployment because of the climate change is rather urgent. And while that is so, the experience so far has suggested that the interest of emerging nuclear energy countries does not fully translate into deployment. And if climate change concern is real, there is an urgent need to rapidly grow nuclear energy along with other non-fossil energy forms. Now, this is actually talking in contradiction. On one side, we know that we have the climate change concern. Other side, we know nuclear is the answer, but it somehow does not grow. And so obviously, there is a need to overcome this dilemma. So obviously, we must understand what are the concerns, requirements of emerging nuclear energy countries, because I think that's where the real growth would take place. Of course, the requirements can be many depending on the energy planning scenario, depending on the requirements of technology, depending on the requirements of human resource. And I'm not going to go in any one of that. But fundamentally, assured safety and manageable liability arising out of large-scale impact in public domain. Now, this is what is at the back of mind. This is what bothers. Many times we confuse between safety and catastrophe syndrome. We may say safety is at a very high level, very low chance that there will be severe impact in public domain. But now that the world has witnessed a couple of them, I think they are unlikely to be accepted. No country will accept, particularly new country. It will take a huge courage on their part to launch nuclear, essentially because of this catastrophe syndrome. Now, getting rid of this problem is essentially more a matter of reactor design, as the advanced heavy water reactor is. In fact, the design or even conceptualization of advanced heavy water reactor was done just following Chernobyl. We had just completed Dhruva reactor and we're looking at what should be the next big reactor that BARC should think about. And that was just around the time Chernobyl had happened, and that's how the concept of HWR evolved. So this is more a matter of reactor design, but thorium plays a role because it adds to a lot of safety strengths, both through its neutronic properties as well as its the thermophysical properties. It's very stable material. It gives some technological difficulties, but that's the advantage of thorium. And so I think it's important that we think about leveraging that. I think the advantages are well known. As I said in the presentation in the last conference in Geneva, I myself talked about it. It has been talked about here, and I'm sure in subsequent presentations there will be many such. So I'm not going to go into this detailed aspect. The second problem is disposal of used fuel, safety and security of that fuel during storage. Now, in the long run, it's very clear to me, recycle is inevitable. I firmly believe that disposal of spent fuel as spent fuel is and will remain an unresolved issue. And I'm prepared to take on anybody who does not agree with this. So this question of open fuel cycle is leaving the world with a legacy of unresolved issue, and I think sooner we come away from that better. But a mechanism has to be evolved to how to move towards recycle. And of course with thorium, one of the concerns with the recycle technology is the proliferation, diversion of fissile material. If you have thorium in your fuel cycle, I think the life becomes much easier. There is much higher degree of proliferation resistance once you have thorium. So life should be easy from that. Then, of course, there is a question of capital investment. Some of the smaller countries would be concerned about having to make large investment for a very large reactor. So that capital investment should be moderate. And so it's better to start with, begin with a small reactor. Unit energy cost, of course, small reactor does not mean unit energy cost can be allowed to go high. Unit energy cost must be competitive, not just with other nuclear options, but any other electricity production item. And that's a must. And we know thorium plays a big role in softening all these barriers to deployment of nuclear energy. And now I come to the specific proposal, which I think, in a manner of speaking, was implicit in what Dr. Sinha said. 220 megawatt PHWR, they are the smallest commercially competitive power reactor today. We can use thorium or thorium LEU combination in 220 megawatt PHWRs. And the use of thorium will offer relatively stronger proliferation resistance, enable higher energy from a unit of fissile material used at higher fuel burn-ups that are now possible. It would offer, the thorium offers better thermophysical and chemical properties for superior fuel performance and enables superior plutonium disposition. So I think the catastrophe syndrome issue probably still remains, but most of the other barriers do get overcome. I already said this, that I have already spoken about this in broader terms. So I now wish to make a very specific proposal in the context of developing countries wishing to start making use of nuclear energy, the emerging nuclear countries. And my simple point is, since the world cannot wait, I think PHWR, along with LEU thorium fuel, can be readied for short-term deployment. And I think internationally it should be considered with, in my view, great seriousness, because this is the option in my view. Now, with mixed oxide fuel containing LEU, 20% uranium-235, and with thorium in the right percentage, so that you have the right fissile fertile mix, we can get comparable utilization of mined uranium in almost every reactor system in commercial service today. But with PHWR, you get the best performance, as is visible from the data given there. With LEU thorium oxide, the proliferation concerns relating to spent fuel are largely addressed, making recycle prompt or deferred. There may be countries who may not like to take decision about prompt recycle, but I think rather than talking about or open fuel cycle or the deferred fuel disposal or option, I think it's better that we talk about delayed or deferred recycle option, and that would make with thorium, the whole thing much more proliferation resistant. And even here, PHWR works the best in terms of the residual plutonium content as well as the fissile plutonium content. The numbers are far, far lower compared to LWRs or BWRs. Of course, there are additional safety advantages because of thorium matrix. And I said it's both neutronics as well as the physical integrity of the fuel. And 220 megawatt PHWR offers the best option because it is the smallest commercially proven system that can favorably compared even with larger nuclear reactor systems. Now, I said it is readily deployable, but some work needs to be done. But this is doable in relatively short time frame. and there are capabilities. Even if you deploy a team of 10, 12 people, they will find answers. First and most important is, of course, because you are talking about a specific reactor and a specific fuel, you need to prove that fuel. So development of LEU thorium oxide fuel for high burn-up performance. It has to be done. But it's a question of doing that work and getting over. And there are facilities available to get this done. One has to, of course, tie up the LEU supply chain. But again, if you talk about in international context, this should not be possible because commercial trade in LEU is quite possible. Of course, we'll have to review the fuel and core management. A comprehensive exercise would need to be done. And we need to also review the reactivity control and safety, the reactivity related safety issues. But this is more an exercise on paper. Now that, according to me, should be the first and the immediate step. But as I told you, that still does not answer the question of catastrophe syndrome. Now that is where I think AHWR comes in. And I think AHWR is also should be almost ready and ready for deployment. Although everybody will say where it is, everybody wants to see that reactor working in the host country. And so it's a matter of few years, I suppose. But after that, one could think of HWR, where in addition to the other aspects, of course, the fuel utilization, it may not be as good as PHWR because the neutronics weight HWR is not as efficient as PHWR. But on all other aspects, and more importantly, in terms of the elimination or minimizing the impact in public domain, we already heard this. This would be a big step forward. So given our vast thorium and solar potential, and of course, given in addition to this nuclear, as I said earlier, we work on development of technologies for energy conversion from nuclear or solar into various other energy forms. And I think we should do that. We should seriously work on that. But if we do that, can India become a net exporter of non-fossil hydrocarbon even as advanced thorium technologies evolve? And I think this is a distinct possibility, and the world needs it. We can join hands with other collaborators. I think that's not an issue. But I think we need to focus our attention on this challenge, because the question of energy does not mean just electricity. I want to re-emphasize that point. And the time has come from global climate consideration that we address this problem as a whole. But of course, while all that is happening, we must develop this advanced thorium systems, whether it's high temperature reactor, molten salt reactor, accelerator driven system, for high temperature efficient thorium use and transmutation of actinides. And I think that's a program that should go on. So to sum up, despite awareness about the impact of CO2 emissions, imperatives of economy and development are leading to growth in fossil energy use and issues of energy sustainability. In India, use of thorium eventually is inevitable. There is urgency to grow deployment of nuclear energy. Use of thorium could soften the barriers to deployment, particularly in emerging nuclear countries. PHWR fueled with LEU thorium oxide can be deployed fairly quickly and with lot of advantage. HWR 300 LEU and the energy conversion technology should be brought in next, while development of HTR, MSR and ADSS takes place. Thank you very much.
Thank you, Dr. Kakodkar. for a very succinctly put the point on a specific agenda which you mentioned. So we have a few minutes for questions, if any. Yes, please.
Takaki from Tokyo. I have a question about India's three-stage nuclear program. In the third stage, the reactor type is not so clear, but you use thorium. For the sustainable energy utilization by using thorium, you can use FBR. You develop FBR in the second stage. You can use this reactor for sustainable energy supply. Is there any possibility to use thorium in a sodium-cooled fast breeder reactor instead of ADS or molten salt or AHWR?
Well, as you correctly observed, what will be the reactor type for the third stage of Indian nuclear power program is actually an open decision, and it's an open decision kept open deliberately. There are many options, and as you said, you can use thorium in fast breeder reactors very clearly. In fact, fast reactors are a bridge between the first stage and the third stage. And so during the later part of the second stage, thorium would have to be necessarily used in fast reactors on a large scale. So it will happen anyway, because without that you won't get the required quantities of uranium-233. So that is it. But having said that, the choice of the reactor for the third stage would depend on several things. The question is, see, fast reactors are good, but the fissile inventory that goes in the core of a fast reactor is much larger compared to what it goes. So with a given fissile inventory, I can set up much larger capacity in the third stage in thermal spectrum. Now, I'm not saying a decision is made, because there are this cost and economics is not constant in time, it varies. There could be also possibilities, for example, with thorium. One of the challenge is a kind of a very good neutron efficiency economy, so that you can on one side convert maximum thorium into fissile material, but at the same time the absorption, for example, in other species, if you have a moving fuel as you have in a molten salt reactor, then the conversion of thorium into uranium-233 is much more efficient. And depending on the spectrum, depending on the energy spectrum, you can actually set up that reactor with much lower fissile inventory. So it would depend on the situation at that time, whether which is the, for example, if ADSS comes through on stream very fast, then this emphasis on fast reactor will not exist so much, because you will get a little growth, at least growth better than what is possible without ADSS. And so that's another option. So it is, in my view, it's an option deliberately kept open.
So if there are no other questions, then let us thank the speaker once again.